Quinine is a bitter alkaloid compound which was used historically to treat malaria. It's also been used in the past to treat various circulatory or nervous system problems, but more recently it's not used as much because it can have a side effect of causing abnormal heartbeat or bleeding and kidney problems. Quinine is also the compound in tonic water, which makes it taste bitter, and I'm going to try and extract it from its natural source, which is the bark of a South American tree called the Cinchona tree. First, I'm weighing out 50 grams of the Cinchona bark. The bark contains a lot of other compounds as well as the quinine. So to begin extracting, the first step is to make it into a kind of tea. I'm adding 350 milliliters of boiling hot water and then stirring to try and dissolve as much as possible. Testing the pH of the solution shows that it is around 5, which is because of compounds called tannins and gallic acid, which is contained in the bark of the tree. These tannin compounds are also the reason that the water goes a deep brown color. In order to hydrolyze the tannins and to neutralize the gallic acid, I'm going to add concentrated sodium hydroxide solution slowly until the pH reaches between 10 and 11. This will convert the natural acids into sodium salts of those acids, which are charged and will therefore stay in an aqueous phase during a solvent extraction. Next, the solution is filtered through a coffee filter to remove the big chunks of bark. I also added another 150 milliliters of boiling hot water just to wash the bark in the beaker and also in the filter. The next step is to use an organic solvent which is not miscible with water to extract the quinine from the solution. So to do that, I am going to pour the solution into a bottle. And then to the bottle add 50 milliliters of dichloromethane. Quinine is going to be a lot more soluble in the dichloromethane than it is in the water, and so it should move from the aqueous phase into the dichloromethane phase. A lot of the other organic molecules and charged particles, like the tannins and the acid salts, are going to be left in the aqueous phase. The reason I'm using a bottle is as a substitute for a larger separatory funnel. My separatory funnel only holds about 250 milliliters, so I can use a bottle and just release the lid to let any vapors of dichloromethane escape and prevent pressure from building up. I let the phases mostly separate in the bottle, and then I decant the top layer into a beaker. Because dichloromethane is more dense than water, the separatory funnel will allow me to separate off the bottom dichloromethane layer from the rest of the solution. You can also see in the separatory funnel that the dichloromethane layer is not entirely clear, and this is because something in the solution has caused the dichloromethane to form these little droplets, and the solution is in between those droplets, so it's pretty impossible to separate it out all at once like this, but I can put the dichloromethane layer through the separatory funnel again, which should remove all the excess solution. After separating off all the organic layers, what I'm left with is a solution of dichloromethane containing still quite a lot of organic materials. The main compound which I want to extract though is quinine, which is an alkaloid compound. That means that the molecule has at least one nitrogen atom. In this case it's a secondary amine, which can be protonated with hydrochloric acid to make a hydrochloride salt of quinine. The hydrochloride salt of quinine is much more soluble in water than its free base form, so I can extract it using water, and then I can convert it back to its free base, which is practically insoluble in water, to recover a precipitate of pure quinine. I transfer the solution into a beaker and then add 25 milliliters of deionized water. Then, using a pipette, I add acid until the water layer, which is the top layer in this case, becomes strongly acidic. Once the solution is strongly acidic, I know that the quinine has all been converted to its hydrochloride salt. It's also important to make sure that the layers are mixed thoroughly so that the quinine has the chance to react with the acid. And testing the upper layer, I can tell that it's quite acidic now. I'm transferring the solution back into the separatory funnel, and this time I want the top layer, and I'm going to discard the bottom organic layer which contains the rest of the organic compounds. The remaining layer is aqueous and contains the quinine hydrochloride. The next step is to convert it back into its free base form and recover the quinine. To do this is just as simple as adding concentrated sodium hydroxide solution until the solution is basic. I've put it against a dark background so it's easier to see the precipitate, and it should form as a cloudy white precipitate in solution. The next step is to filter off this precipitate. Just to check, testing the solution also shows that it is basic. To filter this solution, I'm just going to pass it through a cone of filter paper. It's just a filter paper folded into quarters and put inside of a funnel. Hopefully this will catch all of the precipitate and the solution will just pass straight through the filter paper. I'm rinsing out the beaker with distilled water as well to remove any last bits of precipitate. After removing the solids from the filter paper, I'm left with a small amount of quinine. Something I want to try with this quinine is to see if it fluoresces under ultraviolet light. One interesting thing about quinine is that it can actually absorb wavelengths of light in the ultraviolet spectrum and then fluoresce under those conditions a bright blue wavelength of light. And it does this by absorbing the energy and then becoming an excited particle and then releasing or re-emitting light as it returns to its normal unexcited state. Next I'm going to introduce the samples to UV light. Compared to the deionized water, the quinine solution is fluorescing a little bit blue. You can definitely see where the solid chunks of quinine which haven't been able to dissolve are fluorescing. I managed to extract just under half a gram of quinine from 50 grams of the bark from the Cinchona tree. There's actually a lot of organic compounds in nature which have had a lot of uses in the past and which continue to be used today with limited amounts. I really enjoy doing synthesis and extractions of different molecules, so if you enjoy chemistry, feel free to subscribe to my YouTube channel. And I have a few ideas for some more videos that I want to make.